Okay, this is the third straight talk in this afternoon. It is our pleasure to have許宏彰 here to give us this talk about scanning probe microscopy and its application. Dr. Shi graduated from here, the Department of Physics in ATNU. Then he went to maybe I should let you introduce yourself. Okay. Okay, that's better. Okay, let's welcome Dr. Shi.
Okay, good afternoon, everyone. And I am Hongzhang Xu, and now I work in National Taiwan University and do a postdoc research with Professor Yafeng. So the topic I want to share today is the functional scanning microscopy study of the atomic order material. So benefiting from the advantage of the atomic resolution of the scanning probe microscopy, it allows us to easy to cooperate with the academic and the industry field focused on the material science improvements. So this is the outline. So we start at the solid state physics, and we have the basic information of the lattice structure, and we also can know the electronic structure of the material. So I will explain why scanning probe microscopy can directly get the information the same as the very fundamental information in solid state physics. And so today I also provide the concept of the novel material, which is atomic ordering, and under specific condition, it can trigger new ordering to minimize its energy under different environments. So as a result, it can result in the non-trivial properties and corresponding to the application in its field. So in our lab, we focus on these three different materials. And the first is the perovskite solar cell, and the second is the 2D transition metal dicoconate material. And finally, it also have the 2D ferromagnetic iron germanium telluride material. So today I will use these three different materials to demonstrate the concept I said in this topic, that they have the atomic ordering, and we also measure the new ordering under different conditions. Finally, we also utilize the STM measurement to reveal the non-trivial property of the material. So in the solid state physics, or you want to know some new material, first maybe you can want to find the lattice structure of the material, and you also want to know the electronic band structure, because it allows us to know the electronic property when we want to use it. So in our lab, we focus on the scanning tunnel microscopy, and it's based on the tunneling currents, and it's the tunneling effects. So because we can use the atomic shape apex of the tip to approach the surface, and we can get the tunneling current. And the tunneling current is proportional to the integral of the density of state of the sample, and times the density of state of the tip, and over the energy level we set. And it's also very interesting that the tunneling current can exponentially decay along the direction, and this decay constant and also involve the information of the sample's surface potential. Also, it's also sensitive to the momentum of the density of state. So if we can control the tip into the angstrom scale, so we can get the surface morphology of the sample, and it can reveal the atomic structure of the material. So we can reveal the atomic structure, and we also can reveal the electronic property and involve the momentum information. So these two advantages allow us can directly reveal the sample information, and it's more easy to discuss the some interest property of the material. So the recent consequence utilize the functional scanning probe microscopy. For example, we can combine the two different SPM techniques, such as the STM and the NCFM measurement, to reveal the material property from different fields. And we also can shine the light on the sample surface doing the STM measurements. And sometimes we can use the TIPS electric field to change the surface electronic properties. And doing the cooperate with the industry company, we also design the gate voltage sample to do the STM measurement. And finally, we also have some study because on the magnetic material, because sometimes the tunneling current can respond to the material's magnetic interaction. So, and I briefly introduce the advantage of the material we study in our group. And for perovskite solar cell, it's noted that it has a very excellent conversion efficiency over 29%. And for 2D TMDs, I think due to its 2D intrinsic, in the future we can utilize it to design the 2D channel FET and to improve the performance, and also can reduce the chip size into the nanometer scale. And for 2D FGT, and it's very interesting that the one of iron atom have the interesting property, and it also can cause the diversity magnetic property. And more interesting that some previous work show that the coincidence of the charge ordering and the magnetic order in this material. So use the STM measurement to study this material. We can study the interaction between the magnetic ordering and the charge ordering. So here we utilize STM to reveal the atomic ordering of the material we study. So sometimes it can show the surface reconstruction, and sometimes you can use it to show the atomic defect on the surface. And even you can see the hidden defect below the surface. So it's atomic ordering. So, and this material can have the additional degree of freedom. For perovskite, you can understand the inside molecule dipole can rotate, and the BS3 octahedron can deform, maybe tilt or elongate. And for 2D material, if you stack two layers together, sometimes you can have the different stacking configuration. And for this FGT, the FE1 atom in this material can have different position. Sometimes it can be up, and sometimes it can be down, and sometimes it can be vacancy. So study these materials are very interesting. So how to treat the new ordering in this material? So it's very easy to understand because perovskite is solar cell. So I think shine light on the sample is okay. And is very popular now in 2D TMD, and people have the small angle twister of the between two layers, and it can form the moire pattern, and this moire pattern have the coexisting of the staking configuration, and for 2D FGT, FE1 configuration can result in the spin fluctuation, and this material also have the charge ordering, so we expect it will have the new ordering in this material. So this is the brief conclusion in these two materials, and for proposed gas solar cell, when we shine a light on the surface, you can see the formation of the new structural phase, and it's due to the reordering of the dipole in the material, and this reordering also causes the surface potential change into the one-dimensional electron and the hole pathway, and this pathway is considered as to reduce the carrier recombination under illumination. And for twisted bilayer WS2, and we use STN to reveal the atomic structure of the top layer and the bottom layer respectively. So so from this information, we know the reconstruction type of the twisted bilayer, and we reveal the surface potential variety corresponding to the Mori pattern, and because this material is a staking type, so it can present the interfacial field electricity and form the two equal domains with two opposite dipole direction. So we also use the STN tip with the electric field, and you can see the change of the domain size under change the tip electric field. So today I will more detail to present the interesting behavior of the FGT to see if the additional ordering happen in this material. So, because due to the FE1 atom configuration up, down, or vacancy, so in the STN image, we can see the two distinguished surface, and so next we go to see the atomic structure in the region 2. So you can see three different types of surface structure. The first is the global iron vacancy. So it's from the very clear one-by-one pattern. And the second and the third is due to the up, down, and the down, up, down, up, down, and staking period, and result in the structural loose tree pattern. So it's confirmed that the FE1 configuration in this material. So next we move to the region 1. We want to study in this region because in this region its morphology also shows a very beautiful one-by-one pattern. But in its electronic image, you can see many high point defect in this region. And because it's one-by-one, so we don't consider up-down behavior. So we only consider it as the UUU arrangement of the FE1 atom, and it have the FE1 vacancy in this surface. So here's the detail determine the FE1 vacancy, and we can use the high difference in the is indeed located on the FE1 vacancy location. Also, we have the measurement under room temperature because the energy level is comparable to the diffusion barrier of the FE1 vacancy. So doing the STM measurement, you can see the diffusion of the FE1 vacancy. So what's important of the FE1 vacancy in this UU surface? So previous theory work showed that doing the UUU surface under the FE1 vacancy, the remain FE1 atom can exhibit anti-ferromagnetic interaction, and also it's a triangular lattice. So it will result in the spin frustration. What it means? You can see if in this triangular the spin direction is these two corners, the spin already anti-ferro to each other. So you also want this corner to anti-ferro to these two atoms. So you cannot determine the spin orientation of this one. So it's the spin frustration. So it also means that the system don't like this condition. So how to prevent this condition in the material? So back to the intrinsic property of the FGT family is present the condor lattice behavior. What's the condor lattice? Condor lattice, it means that the conductive electron in the material, which it can anti-ferromagnetic interact with the localized spin and cause the condor screen and reduce the interaction between the localized spin. So when they interact, when they condor interaction, it can form the condor resonance state band nearby